So now let's make some cheese sandwiches. So here I've found a very simple recipe to make a cheese sandwich. So I need 2 slices of bread and 1 side of cheese to make every single cheese sandwich. Now here's a question for you. How many cheese sandwiches can you make with 4 slices of bread and an unlimited supply of cheese? Now I would like you to pause this video and unpause when you have an answer. So if you answer 2 cheese sandwiches, then you got it correct. Congratulations. So how does that work? Well, again, we know that from this recipe, we know in order to make 1 cheese sandwich, we need 2 slices of bread. And since now we have 4 slices of bread, an unlimited supply, because I can't get it to unlimited, so max out 8 slices of cheese. So from that, I can only be able to make 2 cheese sandwiches. So how's that going to apply to what we're going to talk about in this video? Well, I just talked about an application of stoichiometry in food. So what is stoichiometry? Well, stoichiometry, short definition, is moles, the moles concept that you have learned, combining with balance equations. So that is stoichiometry. And the long definition is that stoichiometry is the relationship between the amount of reactants used in a chemical reaction, so what you start with, and the amount of products produced by the reaction, what you end up with after the reaction. And stoichiometry allows us to predict the amount of reactants given a certain amount of product or vice versa. So essentially, why do we have to learn stoichiometry? Why is it so important in chemistry? Well, if we were to do lab, if I asked you to produce something, you probably want to figure out using stoichiometry how many of the reactants do you need in order to produce the exact amount that I asked you to produce, so that you don't overestimate or underestimate. If you overestimate, you will essentially, it's not very cost effective. If you underestimate, you'll have to start your lab all over again. So you probably want to make sure you have the right amount before you start the reaction. So now let's go back to the cheese sandwich stoichiometry problem again. So if you have been given 4 bread, how many cheese sandwiches would you be able to make, assuming that you have unlimited supply of cheese? So again, the ratio here that we look at is we need 2 bread to make 1 cheese sandwich. So the ratio between bread and sandwich is 2 to 1. So now you have double the amount of bread. So you have 4 bread. That means you also need to double the amount of cheese sandwich. So you will have 2 sandwiches instead of 1 cheese sandwich. And of course, we could represent this using dimensional analysis. So I have 4 breads, and the ratio between a cheese sandwich and bread is 1 to 2. That's my conversion factor. So I will have 2 sandwiches after I multiply the conversion factor with the initial amount together. And in this course, though, we are actually not going to set it up in a way that you have to double this and double that in order to do your question. What we are going to use is something called the BCA table method. So B stands for before, C stands for change, and A stands for after. So essentially, in this table, what I want you to have is basically the before, change, and after rows, as well as all your ingredients, your reagents, as well as your final products. Okay, so here I start with 4 slices of bread, and I have unlimited supply of cheese given by the question, so I put XS, indicating that it's in excess, and I will have 0 amount of cheese sandwich before I start to assemble the bread and cheese together. And as I start to make my sandwiches, right, I will eventually use up all 4 slices of bread. And for how many cheese sandwich would I produce? Well, I know that I start with 4 breads, right? And the ratio between cheese sandwich and bread is just 1 to 2. So if you basically combine these two together, you multiply them together, you will get 2 sandwiches. So essentially, plus 2 sandwiches means you're going to produce 2 sandwiches. So in the after row, what you're going to do here is you're going to add the before and change column together. So that should be what you left with, or what you have produced in the end. So here, 4 minus 4. At the end of my cooking, I should have 0 slices of bread. That makes sense. And for cheese sandwich, again, beforehand, before I make anything, I have 0 cheese sandwiches. And now, because I made 2 cheese sandwiches, I should have 2 sandwiches afterwards. So the conclusion from the table here is 4 slices of bread can make 2 cheese sandwiches. So how's that going to apply to chemistry? So let's take a look at a couple of examples here. The first example, if you have 6 moles of oxygen gas, how many water molecules can you make, assuming you have excess hydrogen gas? So for the very first step, it's always going to be write the balanced chemical equation if it's not provided for you. And here we go. We have the balanced equation now. And step 2 is to figure out the mole ratio based on the equation. So again here, like what we have previously talked about, the coefficient here can mean number of molecules. It can also mean the number of moles of substances in that reaction. So we can interpret the ratio here in 2 ways, right? 1 oxygen molecule is required to make 2 water molecules. Another way to say it is if I have 1 mole of oxygen molecules, I can make 2 moles of water molecules. So again, the ratio here is 1 mole of oxygen molecules to 2 moles of water molecules. And then the next step is to construct your BCA table. So to begin with, before you combine the oxygen gas and hydrogen gas together, you should have 6 mole of oxygen gas, which is given by the question. And you will have unlimited excess amount of hydrogen gas. And of course, again, before you combine them, you should have 0 amount of water being produced. And next, what's going to happen is throughout this reaction, oxygen and hydrogen, they are being consumed and water are being produced, okay? So because they're being consumed, the change here is negative, right? So eventually I'm going to use up all 6 moles of oxygen molecules. And for water here, because I start with 0, I start with none, and I'm trying to make more, so it has to be positive plus here. So I have 6 moles of oxygen, and I know that the mole ratio between water and oxygen is 2 to 1. So I can just multiply 6 by 2 moles of water over 1 mole of oxygen, this conversion factor. And in the end, what I'm going to do here is I'm going to add up the before and change column. As you can see here, after the reaction is completed, I will have 0 moles of oxygen left. In other words, all the oxygen gas has been consumed. And as you can see here, as for water, we have 0 mole of water to begin with, and we have produced 12 moles of water molecules. So in the end, in that reaction or in that beaker, we should have 12 moles of water molecules. So now let's take a look at another example here. So if you have 6 moles of hydrogen gas, how many water molecules can you make, assuming you have excess oxygen gas? So again, similarly, first step, write the balanced equation. And then step 2 is to figure out the mole ratio based on the equation. So again, now I'm concerned with hydrogen gas and the amount of water molecules that I can make. So I only need to list out the mole ratio connecting hydrogen gas and water molecules together. And the ratio between the two is 2 to 2, which in other words, is 1 to 1. if you were to reduce it. So here, if you have, again, the next step is to construct the BCA table. Again, to begin with, I have excess amount of oxygen gas given by the question, and 6 moles of hydrogen gas, the same, given by the question. And before I combine these two gases together, I should have none of the water molecules, so 0. And in the reaction, what happened is I'm going to consume both the oxygen gas and hydrogen gas. And for hydrogen gas, because I only have a certain amount, so I'm going to consume it all, unlike oxygen gas. And for water, how many will be produced? Well, I have 6 multiplied by the mole ratio between water and hydrogen gas. And that should give me 6 moles of water. So now what should I have after the reaction? Well, now I should have 0 amount of hydrogen gas being left in the reaction because I've used it all. And for water, I should have, again, 0 plus 6 moles of water because I have none to begin with and I have produced 6 in the reaction. And that should give me 6 moles of water at the end of the reaction. So now let's take a look at another example, which is a little bit more complicated. How many moles of oxygen gas would be needed to completely burn 2.4 moles of hydrogen sulfide? Another word for this one is dihydrogen monosulfide, but I'm just going to call it hydrogen sulfide. And how many moles of each product will be produced? Okay, so again, step 1 is to write the balanced chemical equation. And then we're going to figure out the mole ratio based on the equation. So I have basically the ratio between H2S and O2 is 2 moles to 3 moles. And the ratio between H2S and SO2 is 2 to 2. And H2S, the ratio between H2S and H2O is also 2 to 2. And the next step is our BCA table. Okay, so we are going to list out all our reagents as well as our products in this table. And before the reaction, we will have 2.4 moles of hydrogen sulfide as stated by the question. And we are going to also assume that there's excess amount of oxygen gas. And of course, because we haven't started the reaction yet, so we will have 0 moles of SO2 as well as water. So what's going to happen here is that, again, during the reaction, the reactants are going to get consumed and there will be products being formed throughout the reaction. Okay, so in the end, what we're going to have is you will have used up all of our H2S. And then what we're going to have, and we're going to also use up 2.4 times 3 moles of oxygen gas over 2 moles of hydrogen sulfide. Again, this amount is basically the amount of oxygen gas we're going to consume in this reaction. And as for products, again, we are going to have 2.4 multiplied by the mole ratio between SO2 and H2S. That should give me 2.4 moles of SO2 produced. And it's the same for water, also 2.4 moles of water being produced. So afterwards, what we're going to do here again is to add up the before and change column. So I have 0 moles of H2S left in the reaction. And again, because we don't know what the original amount of oxygen is, so that's not really a concern here. All we want to know is how many moles of oxygen gas we need to completely consume 2.4 moles of H2S. So we just need to figure out the change here, which is 3.6 moles of oxygen needed to completely burn off 2.4 moles of hydrogen sulfide. And as for our products here, there will be both 2.4 moles of SO2 and water being produced, given by the table. So essentially, what you just learned in this video is you have one more conversion factor to work with, which is the mole ratio. which you are going to get from your balanced chemical equation. So you have number of moles of the asked substance, so usually the unknown amount that we are asking you, over the number of moles of the given substance. So the most common, which you have to know how to do this kind of question, is the mass-mass stoichiometry and molarity stoichiometry questions. But I'm not going to talk about these two in this video. I'll be posting another video very shortly for the mass-mass stoichiometry, and maybe in like 2 days, I'll be posting the molarity stoichiometry question type of video. So the summary of the video is basically now you learn the key steps that you need to take in order to solve stoichiometry questions in chemistry. So the first step is always going to be writing the balanced chemical equation if it's not written. And you have to figure out the mole ratio based on the balanced chemical equation. And next, you will construct your very useful BCA table. Essentially, today, the most important thing here is you have now one new conversion factor to work with, which is the mole ratio, which is the number of moles of the substance. Usually, it will be the unknown amount in your question, and over the number of moles of the given substance. So your initial amount, usually. Okay, so that's it for today's video. Stay tuned for the mass stoichiometry video, which will be posted soon.